So this is joint work with Carroll Morgan, Benjamin Kaminski, and Joost-Pieter Katoen. So I'm going to be telling you about a new rule to prove termination for probabilistic programs. So the idea behind the rule is that we want to be able to apply it to programs that make updates probabilistically, and we wanted it to be a generalization of the standard variant rule that people commonly use for proving termination in non-probabilistic programs. So the reason that I've put this as an example program up on my first slide is because even though it looks pretty simple, it's actually one of the hardest programs to prove using a variation of a variant rule. And so what I'm going to show you in the talk today is I'm going to show you, hopefully show you why this is a bit of a tricky problem, and along the way I'm going to show you the idea behind the rule and why we formulated it in the way we did. And then, of course, I'll show the rule and I'll show that it applies to this program along with a few others. So just to make sure that we're all on the same page, I thought I'd just spend about a minute telling you what the termination problem is for probabilistic programs, just in case it's a little bit unfamiliar. So on the left-hand side of this slide, I've got another example of a probabilistic loop program, which is what I'm going to be talking about today. So it's got a guard and it's got a single variable which is either incremented or decremented with some probability. So this is actually saying with probability p, x is increased, and with probability 1 minus p, it's decreased. And obviously this this iterates until eventually the x is set either to 0 or n, so terminating the iteration. So what's happening here is that underlying this process is this probabilistic transition system. So here we have these blobs here are states. Oh, sorry, it's not. These blobs here are supposed to be red, and the squarish ones are supposed to be black. But the squarish ones, anyway, are the termination states, and the round blobs are the states from which termination hasn't yet occurred. And you can see here that from any one of these round states with probability p we can increase, and with probability 1 minus p we can decrease. And of course these states are determined by the value of the variable x. So what happens is that we can look at execution sequences of this program. So this is just values that x can take during iteration of the loop. And so these traces have a well-defined probability distribution determined by these state-wide probabilities. And it's so with respect to that probability distribution over execution sequences, that's where we define the termination program. And what we're looking for is that the set of sequences that have one of these termination states in it, we want to determine whether that has probability 1 or less than probability 1. And so our rule is going to allow us to prove at the program level that distribution over execution sequences has one of these termination states with probability 1. So there is a super nice sort of invariant property of probabilistic programs, which is called a super martingale, and this can be used as as this variation of the variant condition. So the problem with the variant is that it's not always, with probability around, it's not always decreased with certainty, but even so, programs for which NEO variant is not always decreased still, in fact, terminate. So that's where the problem is. So what a super martingale is, it's a function, a real valued function of the state, and it satisfies a bunch of conditions. So it is 0 at a particular state, means at that state the program has terminated. It is non-zero, it's a value greater than 0 on states for which the program hasn't yet terminated. So therefore, using this, you can already see that this is some kind of proxy for how far away you are from termination. So the invariant property is this, that if you look at the value of so I'm using V, throughout this talk I'll use this V for this super martingale function. So what we can do is that, as you saw on the previous slide, for any particular state, there's a probability distribution over next states. And so therefore we can say, well, what's the average value of this V if we allow the program to iterate a single step? And so this V is a super martingale. If that average value is always less than or equal to the value that V was initially. And so I've just worked out for this particular probabilistic program, we can take V to be the actual value that X takes. Okay, so X is some integer valued variable. So we define V to be the value of X, whatever that value is. And so if we look at one iteration of this program and we work out the average value after that iteration, we work out this little equation here. So we say with 1/4 of the time, X has increased by 1. With 3/4 of the time, it has decreased by 1. A little bit of arithmetic shows you that works out to X minus 1/2, which is strictly less than X. So this definition of V is a super martingale with respect to this loop. So you can see that it's a sort of invariant property because that has to hold at every single state for which termination hasn't occurred. And what's super nice about this is, of course, if you figure out some suitable V, and it has this nice property that if you work out if the difference between the average value after a single iteration and its value before is greater than or equal to some fixed epsilon, in this case epsilon is 1/2, then actually this probability theory tells us that eventually the loop will terminate. Well, why is that? I've got a picture of that on the next slide. What's happening here is, so here I've drawn a little diagram of what's going on here. So on the vertical axis is the value of the super martingale. The horizontal axis is the value of the variable X. And you can see that because of this fixed average decrease as it's going, this variant is sort of like a proxy for what's actually happening to the real variable. And so because this is always decreased inexorably, it's saying that if I let this program run long enough, then the average value of this V will be somewhere down here. And the only way that can happen is if termination has occurred. So the new rule is going to be based on this idea. However, there are many programs, including the one that I showed you on the first slide, for which there is no such these is called a ranking super martingale. No such ranking super martingale exists, and so we cannot use this rule to prove that program terminates. And indeed it does terminate because it's just the unbiased random walk. You go to any probability theory book and there's a nice proof in there that shows you that it terminates. So what happens when we don't have a super martingale or ranking super martingale? What can we do? So what we did to try and think how can we weaken this condition, what we actually had to add was something about progress of the variant. And so this is basically how we decided to formulate our rule. So what we did is we weakened the ranking super martingale condition. So we have a martingale or a super martingale which doesn't have this fixed epsilon parameter. And what we're trying to do is we're trying to say, well, if we just have one of those things, what is that proxy thing telling us about the actual behavior of the states, the probabilistic movement of the state space? So the next part of the talk, we're going to have a look at 3 examples. So I'm going to show you 3 examples. So this is the one from the first slide. And the next 2 examples are very like this, but they're changed in only a tiny little way. And what I'm going to do is I'm going to show you why the behavior of this can be coded up in such a way that a progress condition tells us that it terminates, and the next two don't have that property. So this is the one-dimensional random walk. We have a martingale, which is just the value of x. And if you do that little calculation I did before, you'll see it's not a ranking super martingale, because the average of the value of x after one iteration is x itself, so there's no change. However, this does terminate with probability 1. So here's one that doesn't terminate with probability 1. Again, if you just go to to a probability book, you'll see that if the probability of increase is more than a half, okay, then what happens here is that there is a non-zero probability of the x just growing larger and larger and wandering off to infinity, which is why I've called it the drifter. But it does have a super martingale. We define v at a particular state s, determined by the value of x, to be 1 minus the probability that the loop terminates from there. Okay, this is a this is a martingale. Okay, but it's not something that we can actually use to prove termination, which is a good job because it doesn't terminate. However, it is going to tell us something about the underlying behavior, namely that it's going to drift away to infinity. The final program is, again, it's a random walk, but this time we've got this variable here, n, and so the step size gets smaller and smaller. And so again, we can use v equals x to give a martingale. You can check that that is a martingale with respect to this program. Oops, sorry, wrong button. So this is a martingale with respect to this program, but it doesn't terminate with probability 1, because what's happening is that the steps become so small that we get this sort of Zeno behavior, and really the variable sort of stays more or less where it started at. So now let's have a look at what the martingale, so each of those programs have a martingale. What is the martingale actually telling us about the underlying behavior of the program? And this is what we had to do in order to come up with the rule that I'm about to show you in a couple of slides. Well, so here again, here is my picture, and the martingale is 1 minus the probability of termination, so it's this dotted line here, and it's actually bounded. So the further away x gets from its termination point, the more likely it is not to, or the less likely it is to return to the x equals 0, and so 1 minus that probability just gradually approaches 1. So what's happening here is that how we understanding what's happening down here by what's happening up here, if we look at the successive values of the martingale, we see that the further we go away, the closer those values approach 1. So there's like this accumulation point with respect to the martingale. And that, it turns out to be, it turns out that once we looked at this, if you ever have a martingale which has such accumulation points, then those are the things that indicate that the program is not going to terminate. So really, our rule is trying to ban those accumulation points. Let's have a look what's happening with the laggard. Well, the same thing is happening. Again, here is the picture of the variable x, and so this time v is equal to x, so we have the straight line here. So, but what's happening here is again that at any particular state here, if we look at the successive values of the variant under successive state changes here, again we get these little accumulation points, because since x is only being incremented by 1 over n squared each time, and n is always increasing, the value of if you take that collection of those things, then you're finding an accumulation point with respect to the states down here and their values of with respect to the martingale function. So again, the key thing here is that we've got these accumulation points in the martingale. Finally, let's have a look at the program which we know does terminate. And you see this has got no accumulation points at all, because the values of successive, so V is actually the value of successive states, and you can see that they're all totally separated away. So there are no accumulation points. And in these sort of underlying transition systems where there are no accumulation points, that tells us that we're going to have, if we've got a martingale or a super martingale, that's where we know that the program must terminate. So the rule bans any accumulation points, and therefore it bans the first two programs as being able to terminate, and that therefore leaves us a behavior where termination is certain. So this is a informal definition of what the rule is. I'll show you the formal definition in quantitative program logic a little bit later. But so we have a transition system, we have a state space, we have a collection of termination states. We have our super martingale property, and here we don't have that ranking, that epsilon in the conditions for the super martingale. The second point is that now this is where we have conditions which can be validated locally on a single iteration. This was part of what we wanted to have in the rule. So we have two functions, prob, and that is going to be referred to a probability. Dist is going to be referred to the amount of change, the actual change in the super martingale. So these are both functions defined on the non-negative reals. This is a probability, so it's got to be between 0 and 1. This has got to be a non-zero real, because real progress has to be made. So the super martingale has to actually change. But we've got a couple of constraints on these functions. One is that they have to be strictly non-increasing on their domain. Okay? And the second one is that for each iteration, the probability that V is decreased by at least dist has got to be at least prob. Okay? And all of those things can be, so once you come up with the super martingale and these two progress conditions, and you've verified those things, then our rule says that termination is certain. So let's quickly see how these are working on something that we know terminates, and I'll also explain why it doesn't work on those other two examples. So here is the one-dimensional random walk. We've already seen that the martingale is going to be x. The dist function, so for any real that's going to be 1. Why? Because the change in the super martingale is always at least 1, because it either increases or decreases by 1. Secondly, the probability that happens, that the super martingale changes by at least 1, is always a half. And you can see clearly that these are non-increasing, and also you can see just by sort of inspection, informal inspection, that the super martingale changes by at least a half. The probability that it changes by at least a half is a half. So this rule, therefore, that's therefore quite easy to show that this, therefore, does terminate. What's happening here, though? So here I said that there is a super martingale, right? So this is 1 minus the probability that it terminates. So now let's try to define a dist condition here. And what happens is that for any real value at least 1, we find that because of the non-increasing condition, dist r has got to be equal to 0. And I said part of the conditions of our dist was that dist has got to be non-zero everywhere, because some non-zero distance has to be moved. The super martingale has to decrease by at least some non-zero distance. So we can't define a super martingale, these prob and dist functions with respect to this super martingale. And this is related to the no accumulation points, because in fact there is an accumulation point which is the thing preventing us defining that distance to be greater than 0. And in the proof of the rule, the no accumulation points is absolutely essential. So, yeah, sorry, I've done that one. So the next one happens for the same reason, that again, we have this super martingale, but there is an accumulate. If we try to define the dist function, we find that dist has got to, as n gets large actually, then the only way to define that dist function is to have it to be 0. So this is the formalization of the rule. So I'm not going to go through this in detail, only to say that it's formulated in quantitative program logic. So this is the quantitative version, it's a quantitative version of pre-post reasoning. This is the super martingale condition, and here it's only determined by the, so this is the while guard iteration. So this constraint is only, it can be validated just by looking at the probability distribution over states. And similarly, this is the P, or the prob, and the dist condition, again, is formulated just by looking at the iteration. So just in the last minute, just for fun, I just want to show you two other programs that works for this. So this is a loop where, in fact, the probability of decreasing and increasing changes with respect to this variable x. But again, it's another random walk. And so this does terminate. And what's sort of quite nice about this is that the probability of increasing is always at least a half, although diminishingly so the further that we get away. And weirdly, this does terminate. And here is the conditions that we have. So the V is actually the nth harmonic number, which you can give a formula for, and we've done that in the paper. The dist is 1, a half, a third, and so on. And the probability is 1/3. And again, you can check all of those with respect to a single iteration of this thing. So this was quite weird, and we did find it in a probability book, which proved it separately that it does terminate. So that was happy about that. And finally, I just want to say that this rule works for non-deterministic probabilistic programs. So the logic is set up so that it actually works quite easily for that. And again, this is just a non-deterministic version of the fair Walker. So, final comments. The proof rule applies to programs, both probability and non-deterministic. We took away the epsilon and the ranking super martingale, and we added constraints on probability and the distance moved. Although almost sure termination was is what I've talked about in the talk today, the full proof rule allows us to prove quantitative properties. So the termination is really a precursor to be able to examine quantitative properties. And we have thoughts on completeness, but it's very hard. Thank you very much.
Let's thank this. So if you have questions.
Yeah.
Maybe you can. Is it working now? Okay. So it seemed like you went from the expectation to the variance, to the next moment. Is there actually, does it make sense to go to the next moment? Does it maybe lead to some completeness?
It could do, but I haven't sort of thought about that. And as I say, the rule that we haven't considered completeness, and it might be that we have to look like there for.
And the second question is about what you mentioned about non-determinism when it's added. So in non-probabilistic programs, when you have non-determinism, you could need ordinals, so you need something higher than just the natural numbers for ranking. Is there some analog of ordinals in here?
I suppose so, but I haven't, you'd need arithmetic on ordinals, so yeah.
Let's discuss it later.
So let's have one more question.
From CMU. So I have a couple of questions. So the first question is, actually in the talk, so you propose new rule for proving the almost sure termination of the probabilistic program. But to do that, so you have to find the variant and also invariant. So V and I, okay? But actually the question is, do you have any way to automatically generate the set of invariant I and the variant V?
No.
Okay. So because if not, so I think the approach is not very practical in practice.
Well, I mean, it depends. I mean, you can say that for the variant rules in even non-probabilistic programs. Some variants that I've seen are weird, right? So, but if you want an actual certificate to prove it, then it's a problem of the variant.
Yeah, and also in the formalization, so you want to check that so the variant V satisfies the super martingale's property. But in the formalization, I see that you prove that the S, the maximum of 0 and S minus V is a sub-martingale. So why you go the right?
Yeah, that's because the formalization included taking non-determinism into account. And whenever you look at probability books and you see super martingale, it's the way that I showed you in the talk, which is why most of my examples just had probability in.
Yes.
Yeah, it's to deal with the
sorry, but
non-determinism.
I suggest that you take this discussion offline because we have to.